Okay, today's talk thumbnail looks kinda confusing and like very technical, but let's see. So we are up and running. That's looking good. Is this updated? Yes, it is. Okay, cool. So welcome back to this advertisement episode for Lasergurkenland, reachable under lgl.cityhun.com. It's a vanilla anarchy server, and I don't feel like doing a super long introduction today. So if you want to have more details about what this server and this live stream is all about, I mean, I can tell you what it's all about. It's all about advertising the server, but why you want to play on the server, or what's the server all about, I mentioned that in a lot of other episodes. Okay, cool. So yeah, without further ado, I would say let's get right into today's talk, which, as I said, had a really confusing thumbnail. It's about exploiting PHP7 unserialize from the 33C3, and my pronunciation today is, as always, on point. Yeah, so many mobs, please send help. Okay, so it's a video from 2016. It currently has 3,000 views on YouTube, and it's uploaded on the media.ccc.de channel. Link to the video is, as always, in the description. And if you want to have better audio quality, I don't know, my audio quality should be kind of fine, but better audio quality, and you want to see the slides, go check out the original. If you're interested in this Minecraft server, go get your latest premium, like it's not cracked, Java edition client. It can be a hacked client as well, and join on the server and have some fun. So yeah, let's go. I will mute myself now. Am I still muted from the last episode? No, that's awesome. So you actually heard what I was saying in the introduction. That's very useful. Cool. Yeah, then I will now mute myself, and you will no longer hear my annoying comments during the talk that you might be used to if you actually saw all the videos on this channel. But due to the audio quality improvement, I decided to mute myself. And let's go.
Okay, good morning. Good morning. Welcome again to our second talk of the day. Our next speaker is a security researcher at Checkpoint, and he will be talking to us today about exploiting PHP7 unserialized mechanisms. So please give a big warm round of applause to Yanai Livne.
Okay. Hi. Welcome to my talk, teaching the new dog old tricks. It's about PHP7 memory internals for security researchers. And I must give a disclaimer first. This is not a talk about PHP code. It's about PHP7 interpreter. So I hope you enjoy it. About me, my name is Yanai. As already said, I work at Checkpoint. My team and I work about many stuff, and networks, embedded devices, exploit sites, client sites exploits, but also memory corruptions of all sorts. And today's agenda, first we'll have a brief introduction about PHP, and then we'll talk about PHP unserialized mechanism. After that, we'll talk about the implementation of the zval system, the value system in PHP7. Now, gaining this knowledge of unserialized and the zval system, we'll see some bugs and vulnerabilities. After that, we'll discuss the internals of the allocator in PHP7. It's a new allocator. And using our knowledge of the allocator, and we can see how we can exploit the bugs and write remote code execution exploits. Then we'll have conclusions, questions, etc. So let's begin. PHP is the most used language in web applications today for writing web applications. And basically, it's server-side language, and servers rule the world. All our information, all the data we have in web applications is in the server side, so it's very interesting as malicious attackers that want to get some information to attack the servers, usually. And when I said it's the most used language today, the most popular version of this language is version 5. But in the last year came up a new version, was released, PHP7, and this is what we're going to talk about today. So it's one of the most important languages today. And what about the security of PHP and PHP applications? Well, like every popular language has vulnerabilities written into it or written by it. So we know many vulnerabilities of SQL injection in recent years and XSSs. These are high-level vulnerabilities, and it depends on the code you're writing to your web application. But there are also memory corruptions. How can you have memory corruptions in high-level language, you ask? Well, some of the functionality of PHP is implemented in the interpreter itself, which is written in C. And when you pass user input to this kind of functionality, and you have bugs there, you can get some memory corruptions. The most notable example for this is the unserialize function, which has been exploited many times over the recent years. And this is exactly the function we're going to talk about today, but in the new domain of PHP7. So what about the history of unserialize? Well, too many CVEs, actually. And most of these vulnerabilities were exploited in object injection, so property-oriented programming, if you heard of it. And this is a logical exploitation. It depends on the application that is used, how this application, the PHP application, was written. But there also have been memory corruptions. And memory corruptions does not depend on the application. Memory corruption exploitation depends only on the PHP version. As I said, version 5 or version 7. And for memory corruptions in PHP 5, there was a generic exploit developed by Ionic, Stefan Esser. It was described in Black Hat 2010. And this exploit could basically work on every PHP 5 memory corruption, unserialized memory corruption you had. So, as I said, it's a very old problem, but here is an example from this year, on July. This small website, I don't know if you're familiar with it, opened the bug bounty, and this bug bounty attracted attention of a company called Evonide. They looked at the API and found this API call, a post request, and you can see a cookie here, and this cookie has a very interesting format. This is the format of unserialize. And of course, when you send the request, you get a response, and you see that the server will actually process this cookie. So we have a vulnerable unserialize right there. And what they did, they fuzzed unserialize in version 5 in this instance, and found a new vulnerability, exploited it, got the bounty. So what about PHP7 I'm talking about all the time? Well, it's a new release of the language. It was released just a year ago. And they kind of re-implemented everything for performance. So they re-implemented the value system. They have re-implemented the memory allocation mechanisms. And for this reason, the exploitation technique of the memory corruption does not work anymore. Exploitation of memory corruptions depend heavily on the memory layout. And when you change all of that, nothing works again. But still, we have the unserialized functionality in PHP7 because you have some sort of backward compatibility. And there have been some CVEs. Object injection still works, being purely logical. But the memory corruptions, while still there, you can still find memory corruption vulnerabilities in unserialize. You don't have any remote exploits until this talk, more or less. Yeah, thanks for me. So let's talk about unserialize. And unserialize, first, we have to, I have to make something clear. You should say deserialize. Unserialize is grammatically incorrect. And if it bugs you, well, that's how it's going to be for the rest of this talk. So I'm sorry. But PHP being PHP, we can go on. And this is the documentation of the serialize and unserialize functionality in PHP. Basically, what serialize does, it takes values and converts them to a string that you can store and retrieve later. And unserialize is the reverse operation. So you get a string in a specific format of unserialize, you convert it back into a value. This is very simple, you would say, but there have been too many vulnerabilities there, and we'll see exactly why. So let's have an example of serialization. Okay, assume we want to serialize this nice array that has another array inside of it, and so on. And we'll go step by step and serialize it to the to unserialized format. So first, we're serializing an array with 4 elements. So as you can see down below, we have the string, and it's a colon 4. A for array, colon 4 for 4 values. And in PHP, every array is actually a hash table or a dictionary. So it's a key value store. But when you have an array, it's the keys are implicit. The keys are just a running index, and it's implicit. So we're serializing the first entry. It's integer 0 as key, so you have I colon 0, and null for the value. Next, we're serializing integer 1 for key and integer 1337 as the value. And then we're serializing a string. So we have integer 2 as the key, and string. So we have S for string, colon 5 for 5 characters, then we have apple. This is the value of the string. Next, we're serializing another array. So we have the implicit key integer 3, and the value A colon 3 for 3 values in this nested array. Next, we have an explicit key, string A, so we have S for string, colon 1 for 1 character, A for the value of the string, and this is the key, and the value is integer 1. Next, we're serializing a class, an object, actually, so we have, we're going back to the implicit keys, so it's integer 0 as an implicit key. Then we have object that the class name has 8 characters, so it's colon 8, colon the class name, std class. Then we have colon 0. 0 is the number of properties in this object. 0 properties, nothing in there, curly brackets with empty properties. Then we're serializing integer 1 as key and integer 7331 as value. And this was the process of serialization. Quite straightforward, and we have this nice format that we know about. Next, I want to show you an example of unserialization, and this would be the exact reverse, so it's going to be a bit boring, but I want to show something here. PHP supports a feature called references, and references means that during unserialization, in the format, we can specify, instead of specifying a value such as integer or a string, we can specify a reference. And this tells the PHP mechanism, go back, see what was the nth value we just parsed, we just unserialized, and I want a copy of this value or a reference to this value. And in order to support this feature, during unserialization, every value that is parsed by the unserialize mechanism is kept a reference to. So we have this array called the var hash array, and in this array we have pointers to every parsed value. And let's see how it's done. So first we're unserializing an array with 4 elements. So you can see in the var hash array, and it's a 1-based array, you have pointer to this array we just instantiated. Next we have a key integer 0 and value null, and we can see that the second pointer points to the null we just parsed. Next we have integer 1, key integer 1337 as a value, and the third pointer points to 1337. Then we have the string apple as the value, and the fourth pointer points to this value. Next, we have this array. Now, this is an eternal array, but the var hash array is a flat array. So even though we have some nesting here, we have array within an array. In the values are nested. The var hash array is flat, and the fifth pointer points to the array. Next, we're unserializing the key a and the value 1, and we have another pointer to the value. Then we're instantiating the std object, so we have another object there, and the 7th pointer points to this instantiated object. And now something interesting is going to happen. We're unserializing a reference to the third value. So what would happen here, PHP, the unserialized functionality, will go and check the var hash array. Go to the third value. The third value here is a pointer to the integer 1337. And now we need to create a reference to this value. So this is what we do. We unserialize this value, and we create a reference to a previously parsed value. So this is how PHP supports this feature of references, of backward references. And this mechanism, this feature caused many bugs in the past because, as you can see, we keep pointer to stuff we maybe need, maybe we don't need it again, and there has been some confusions over the years. If you've gone lost in this complicated format, there are some points I want you to remember. So first, it's a complicated format, okay? Yes, obviously, and complicated formats leads to bugs. And this we're gonna see it soon. we have many ways to control allocations, right? We're instantiating objects, we're unserializing strings of various lengths, we're unserializing hash tables of various lengths, so we have lots of control as users. And we keep these references things, so we keep references backwards to things we unserialized in the past, and we can reuse them. So in this case, we have some use after free, we managed to free some object in some magical way, we still have pointer, and we can go forward as exploiters. So now we talk about the zval system in PHP. Now zvals are basically values, okay? This is how the PHP interpreter calls values, or holds variables. This is a PHP variable. I'm sorry that we have PHP in this talk, but there won't be much of it anytime soon. And as high-level language, we have a couple of features for our variables. One, we have automatic memory management or garbage collection, and we have this references. Reference, when y is a reference to x, it means that the value of variable y changes when the value of variable x changes, and vice versa. So they both basically are variables holding the same value. And this is how the zvals were implemented in PHP5. We had this struct called zval struct. It was on the heap. It was reference counted. And every zval was basically a pointer to this struct. And every time we created a new zval, we had to allocate this struct on the heap and initialize it. The memory management was quite obvious. We have reference count and we have memory cycle detection. So it was a very simple algorithm, which most people know about. And to make references, to make two variables point to the same value, was just two pointers pointing to the same struct on the heap. Everything was very simple, very nice. But it was slow. So when implementing PHP7, there have been some motivations to change it. And the implementers wanted less dereferences. Now, if zval is a pointer, every time you need to reference a value, you have to dereference the pointer, which can be expensive. Also, every time we create a new value, even if it's for a short time, even if we know exactly where it is, we still have to make allocation on the heap, which can be expensive. So they designed a system for embedding. They said, okay, I don't want zvals to be just on the heap, I want to be able to embed them everywhere I want, on the stack, in other structs, and so on. And this is how the new zval system is implemented. We have this zval struct, but now it's a bit different. It's simpler. Zvals are just this struct, and this struct contains only value and type. So there's no reference counting, and we can put this struct wherever we want. And the value thing here can be one of two things. It can be a primitive type, for example, a primitive C type, like integers or floats and so on, but PHP supports also strings. So if you want to support complex types like strings or objects, this value would be a pointer to a complex struct, and this struct will be on the heap. Okay, so this struct will not be on the stack, it will be somewhere on the heap, and it will also be reference counted. So here's an example. This is an integer, and in memory we'll just have the value 1337 and the type long. That's it. We don't know where it is, and it's quite simple. Now, to support reference counting, now it's the responsibility of whoever initialized the zval, right? If the zval is in a struct, whoever initialized the struct needs to clear it up. But there is one complication here. If the value is a primitive value, everything is good. But if it's a pointer to another struct, this struct should be reference counted. And when it's reference, and this is how the garbage collection works, it checks the value pointed by the zval, and it has also reference count and garbage collection. Now let's see an example. Okay, so this is the string struct. As I said, it's a complex type, so this struct is on the heap and is pointed by a zval. as you can see, the first field in this struct is the reference count, and the last field is a flexible array member member. So when allocating a string, we allocate more data, enough memory to store the string content itself, and we access it via this field. So this is what it looks like in array when we're initializing a variable of type string. Then we have the zval struct, it's of type string. We're allocating the Zen string on the heap. We initialize it with the value. As you can see, we put the value apple here. And we just point the zval to this string, and the reference count is 1. And this struct is on the heap. So how can we manage the references? Did the references feature was implemented? This time we cannot just make one zval point to another because they may be in different scopes. One can be in a struct, the other can be on the stack, and they must be managed, right? So there is a solution here. In PHP, they implemented another type called references. And it's easier to show than explain, so I'll show how it works. Assume you have this variable x, which has 1337, and now we have the variable y, which is a reference to variable x. Okay, so we have it in memory, and now I want to make a reference to it. So we initialize a new struct, okay, on the heap called the reference. And this struct has two fields. The first field is a reference count, and the second field is another zval. And we initialize this zval value to be the same as x. So you can see it contains a copy of the value. Then we change the type of x to be a reference, and now it points to the Zen reference. And now we can initialize y, and y will be the same. So it will also be a reference to something on the heap. So we moved the contents of x to the heap, and now we can have the two zvals, x and y, be just pointers to the heap like previously. The key things to remember about zvals is that they're designed for embedding, so they can be in many places, which can cause some bugs. The motivations or goals were achieved. There are less dereferences and less heap usage, but making a reference is a bit complicated. Reference is not a feature that it used too much, except in exploits. So this, there is a trade-off here between zvals are now more simple, but references are more complicated, and it's a worth trade-off, in my opinion, at least. So now that we know about unserialize and we know about zval, let's see some bugs and vulnerabilities. So first, the use of an initialized value. Now, since zvals used to be pointers, initializing pointers was very easy, right? Everybody knows how to initialize a pointer. You just point it to null and you're done. Initializing structs is a different story, right? We need to initialize them with some macros or maybe some constants. It may take some time, and programmers tend to skip this phase if it's possible. You don't initialize your structs, which is a problem, and this is can lead to some vulnerabilities. And this is the exact example here. We have this function, the SPL object storage unserialize. And this function is the custom implementation of unserialization of the struct SPL object storage. This class is implemented in C code. Some of the classes in the SPL, the PHP standard library, are implemented in C, and this is the case here. And as you can see in the first line, two variables are declared, entry and inf. These are zvals, so they're of type zval struct. And at no point in this code they are initialized. And after a few lines of code, we reach this statement calling the function PHP var unserialize. This is the C implementation of the unserialize function. And the first value is a pointer to this inf that was never initialized. And this is supposed to be an out variable. But it's not, okay? But this is where we're going to store the string we're unserializing. The next variable is p. P points to the string we're unserializing. So this function, what it does, it unserializes the string pointed by p and stores the value in inf. However, internally, we reach this line of code, zval pointer destroy, which means please destroy the zval which is pointed by rval, right? And what is rval in our case? It's inf. It's exactly the thing we did not initialize at no point. And the reason the code does this is to make sure there is no value in this zval before writing new values. But since this value was never initialized, what's in this value is garbage from the stack. And if you shape your stack correctly, you can cause some bad things to happen. So this was CVE 2016-7480. Okay, so the next example is type confusion. And we are going to rely on the fact that making references is a very complicated process, as you see, and it changes the type of the zval, okay? And we can suspect somebody forgot about this possibility, and this is exactly what happened. So we have the same function again, and this is, you have more lines of code from the same function, but it's the unserialize of the SPL object storage. And as you can see in the second line here, we are calling the internal unserialize, and we're again converting the string pointed by p and store the result in the zval entry, okay? 2 lines later, we're checking the type of what we just unserialized, making sure it's of type object. So you can see that if the type of entry is not object, the function bails, bad things happen. But if it's, nothing should happen. But if it's of type object, we can go on. And in the last line, we're unserializing the next value. P is advanced here, and now it points onwards in the string. And we're converting the string pointed by P and store it into inf. But what happens if inf is actually a reference to entry? Well, the type of entry is going to change. And let's see what happens. So first we're unserializing entry. And it's an object. And we're checking. And this is actually an object. And everything is good. But next we're unserializing inf. And inf is a reference to entry. So according to the process, first we're allocating a Zend reference on the heap. And we're initializing to be the copy of entry. Then we're changing the type of entry to be of type reference and point to this reference. And of course, lastly, we're initializing inf. But in this process, we actually changed the type of entry after we checked it. So this is a bug, and actually bad things happened. It's not exploitable, but it's still a bug, and it was fixed. So this is bug 73258 in PHP system. Okay, so this is the last bug for today, and it's a use after free. And the problem stems from the fact that now zvals are embedded in structs. And we keep pointers to these zvals, but structs have their own rules of how they change. And some structs tend to change the place in memory without telling anything else. And if we keep using these pointers, we're actually pointing to a memory which is not valid anymore. So such a dynamic struct can be a hash table, for example. And this code is the process nested data function. This function is the function that processes every hash table during unserialization. And hash tables can be also properties of an object. Okay, and here in the first line, we're declaring the variables. And the next line, we're adding a new entry to a hash table. So what we do here is Zend hash add new. We're adding a new entry. The first parameter is the hash table. And the second parameter is the key. And the result of this function is a pointer to the zval that is the value. So we get data points to this zval we need to fill. And then we're calling the last line. The last line calls the internal implementation of unserialize. And again, it converts the string pointed by P and stores its value in data, where data is pointing to. But look at the last parameter here. It's the var hash, this array we talked about in the previous part. And var hash keeps pointers to every piece of info, of every value we parsed, including data. So data points internally to the hash table, and it is stored in the var hash array. But what happens if we manage to insert another value to the hash table? Then the hash table might resize, right? Hash tables grow sometimes in memory. And when they grow, internally they reallocate their memory to store additional values. So this is how it looks like in memory. First, you're unserializing an object. And this object has some properties. For example, it has 2 properties, 0 and 1. And then, magically, we manage to insert another value to the properties hash table, and it reallocates. So now the var hash points to the new value that was unserialized, but the 2 previous values are not valid anymore. And this is not very common scenario. It's quite hard to exploit this or to trigger this vulnerability, actually. Because if you remember the format, before unserializing an object, there is the number of properties in this object. And PHP makes sure the hash table has enough capacity to hold all these properties. Yep. There are two ways to trigger this vulnerability. The first one is the wake-up function. And this is a function that objects can define. And this function, this method is called after the object has been unserialized. And if, for some reason, this function defines a new property on the fly, then the interpreter is not aware of this beforehand. So inserting a new property on the fly can cause this, that can trigger this vulnerability. And also we have my all-time favorite object in PHP, or class, the date interval class. And this class has a very interesting behavior. It does not initialize its properties hash table beforehand. Or it actually, only when accessing the properties of this object, then it defines and adds its properties to the hash table. So if we manage to come to some functionality, such as toString or wakeup, that touches this object or some object's properties, such as date interval, we can trigger this vulnerability. And this was CVE 2016-7479. So these bugs are complicated. There are still unserialized vulnerabilities. Even between the time I submitted this talk and today, there has been at least one more that was reported and published. The vulnerabilities are a bit different than what we used to see, because the ZVal system is a bit different, but still memory corruptions. And these vulnerabilities let us use freed values, as we've seen. The two vulnerabilities let us reuse the freed values, and this is a property that we're gonna need in order to exploit these vulnerabilities. So after we know about how the system works internally and how the ZVal system works, and we found some bugs, we're gonna talk a bit about the allocator. Because when exploiting this kind of memory corruption vulnerabilities, we need to know how the allocator works, how memory looks like. So we had the previous allocator of PHP7, and it's not too important, but it was heap-based allocator. And every slot is the allocation unit in PHP. Okay, so it's called slot, and it has a size and flags to each allocation, and also a free list for caching. And it was very fun, and it was nice for exploiting. But now we have a different allocator. The allocator here is it's a complete rewrite. There is nothing similar, and it features beans or memory pools, as you know them, and free list. This is basically how the allocator works. These are the basic building blocks. And now I'm going to throw some details at you, and you will probably see them or not. The allocator works in chunks of 2 megabytes from the operating system, and these chunks are divided into pages. The first page is page descriptor. It describes the chunk. It has a couple of structs. The two important ones is the one describing the pages, which pages are used or free to use, and pointers to the bins or to the free lists that were initialized. And every bin is a free list of specific size. We have the 32 bytes bin, we have the 16 bytes bin, and it can span over multiple pages. Now, let's say it in a way you can actually remember. So here is a chunk from the operating system. It's of 2 megabytes, and it is divided into pages. First page is the chunk descriptor. You can see the free slots. It is just an array of pointers to free lists and page info for each page. And this is what a bin looks like. So bin, it can span over multiple pages. This is the 16 bytes bin, and we initialize it as a free list. So every 16 bytes points to the next bytes, and we register it in the chunk descriptor. So we have the page information, 16 bytes, spans over 2 pages, and pointer to the free list. Now, the allocation algorithm is quite simple. First, assume we want to allocate a slot of size 30, then you check to which bin it belongs to. I think it belongs to bin number 5. Then we check if there is a free list available or is a bin initialized. If there is no initialized bin, we initialize a new bin, and then we just pop from the free list. So assume you want to allocate 30 bytes. There is no 30 bytes bin available right now, so we're initializing a new bin, and then we just pop from the free list. Assume you want to make another allocation of the same size. It's even simpler. You just pop from the free list. Freeing memory is the inverse operation. So we get some pointer. We want to free it back to the pool. So we check to which chunk it belongs and which page within the chunk it belongs to. We read the chunk descriptor to know to which free list to push it back, and we push it back to the free list. So assume we want to free the first slot of this bin, then we just see it belongs to the third page. We see the third page is of bin 32. We go to the free list and we just push back. What I want to remember about the allocator is that the allocator is very, very predictable, which is important for us as exploiters. And it's impossible to free just random pointers. This was used in the previous exploitation technique, but it's not possible anymore because we have some bit operations and lookups, and it's hard to forge memory to look the correct way for this to work. And we can abuse free list pointers to get arbitrary rights. So we can change them. If we can change the free list and then allocate few slots, we can allocate to the place we want to, and I'm going to explain it much more later. So now that we have vulnerabilities and we know about the allocator and how it works, it's time to write an exploit, right? And every exploit has a few stages. The most common one are leaks, so we want to leak some memory information to bypass the ASLR. Then we would like to read some memory, so we can read data or gadgets, function pointers, so on. We would like to write, maybe write our shellcode, maybe write some other stuff, and we would like to execute code. This is what we're here for. And first thing, we're going to talk about the leak. I think it's the most complicated part. And we're going to abuse the allocator. It's our best friend here. It's roughly based on the previous exploitation technique, but it's a generalization of it. And we're going to use our ability to serialize freed objects, and we believe we can serialize free objects, not only use them, because this is how we initially started, right? We have unserialize. If we're unserializing something, it was serialized before. So we have some kind of a mechanism here that we serialize something and serialize it back, and so on. The allocator, if you remember, is a free list, so it overrides everything that is passed to it. So if we free pointers, the allocator is going to free slots that the allocator is going to override them. And after we free and we use them, we can read via these pointers and read some data that was also freed. So this is how it's going to work. The allocator is a free list, and the first pointers in these slots, in the free slots, is the next slot. It's just a pointer, right? So here is the free slot struct, and you can see the first field is a pointer. And when we read freed objects, we can sometimes read via this pointer. I mean, we freed the slot, and we're still using it, so we can read via this pointer and read to the next slot, next free slot. So here is my all-time favorite class in PHP, the date interval class. And as you can see, this is how the struct is implemented in memory, and the first field is a pointer. How lucky we are, right? And it points to this struct. And this struct is a very simple struct. It has many fields, but all of them are integers. They're not only integers, SLL is signed long. So they're also unserialized and written back to the user. So when unserializing this class, we're actually getting these numbers, the year, the month, the day, and so on. So how are we going to forge a leak in practice? First, we're going to allocate this date interval, and we will allocate an object to leak, for example, a string. And then we're going to free both objects, first the string, then the date interval. And the allocator is going to override the date interval with a pointer to the string, to the freed string, because this is how it works. And the allocator is also going to override this string with some pointers. So when we serialize this date interval, we're going to read these objects. And here is some hex dump for you, because you really wanted it. And here is you can see the free list before we start our exploit. And now we allocate a date interval. And as you can see, it points to some struct that I initialize with -1s because it doesn't matter so much. And we're also allocating or unserializing a string, one after the other. And now we're freeing the two of them. And as you can see, the date interval pointer, the first pointer, now points to the freed string. And when unserializing this date interval, we'll actually get the values in the string. We'll get these pointers as integers, which is very nice. How can we read memory? Well, we have this very nice struct already. So if we can control this struct fully, if we can control a zval fully, we can just change this pointer to whatever we want. So pointing the first field in the date interval will let us read any kind of memory we want. If we don't control as eval fully, which can be the case, in 64-bit it was the case, there is a more complicated way, and I'm not going to discuss it here, but basically we can use a different object, the date period object, which has a first field as a pointer, which points to another struct, and in this struct we control another pointer that is passed to strcopy on unserialization. So we can read memory with strcopy, and you can see all the details in the paper I published earlier this year. I'll give you links in the end of this talk. How can we possibly write memory? Well, writing memory is much more complicated here. And this is what we're going to do. We're going to free some strings back to the allocator. And in the strings, we're going to write pointers to wherever we want, whichever memory we want to write. Then we're going to abuse the free list. And we're going to change the pointers in the free list and going to increase them or decrease them depending on our vulnerability onwards in memory. And at some point, if we increase them enough, they will actually point to this memory we want to write to. So after a few allocations, we'll actually have the memory allocator give us the address we want to write to. And this is exactly what we want to happen. So how can we free these strings? As we said, every value we're parsing in unserialize gets a reference in the var hash array. So we have reference to almost everything, and nothing is freed during unserialization. Except there is one exception, and it's in the hash table, we can use the same key twice. Keys are not kept references to. And if we're using the same key twice, and the keys can be strings, the second time we're using this key, it is freed. The hash table looks at the key and says, I've already got this key, I don't need it anymore, and frees it back to the allocator. No references to it are made, and it's back in the allocator for us. And the next thing we need to know is how to abuse pointers in the free list. This is the most interesting part here. And the reason it's possible, and it's very common, is because we have type confusion here, right? We have the free slots, which their first field is a pointer, but we also have something that was freed, the value that was freed, and we still have a reference to it. And on the heap, every struct on the heap has a reference count, and the reference count is always the first field. So if you take the Zend object, for example, this struct first field is a reference count. So if we have a type confusion between an object, so not a type confusion, but if an object was freed and we can still use it, increasing the references or decreasing the references to this object actually increases or decreases a pointer. So this is how we can control this pointer. And some more hexdump. So this is part of the exploit I wrote to bug 71311. And here you can see that we already freed the strings back to the allocator, so you can see the 4 ones in the hex dump. And now we're going to trigger the vulnerability. The vulnerability here lies in the array object class, and parsing it increases the pointer in the free list by 2. And now we have use after free of this address, that is pointed by the free list. It's still in the allocator, but we have a reference to it. And it was the 11th value that we parsed. So adding references to this address, so R11 parsing R11, so on, we're increasing this pointer by 2 every time. And at some point, we reach the values we just freed back to the heap, or back to the allocator. So now if we allocate twice from this bin, the first time we'll allocate the object that was corrupted, and the second time we will actually can write to 414141, and we will segfault. But this is exactly what we wanted, right? So code execution. After all this, code execution is quite simple. If we're controlling as evil, as I said, the easiest way is to override a callback, right? You control some object, you can decide what callbacks it has. But if you don't control as evil fully, you can just, we have a write primitive, so we can write the function pointer, and that's about it. So, takeaways from this exploit. The allocator is your friend, please use it wisely. And these primitives are reusable. They can be used in many different vulnerabilities within the unserialized mechanism. And combining all these primitives, you get a remote code execution. Conclusions from the talk. Even though you're writing your code in high-level language, such as PHP, you're still vulnerable to memory corruptions or other low-level problems. The new design of PHP is for efficiency. You still have vulnerabilities. I don't think it's more secure or less secure in a way. And the allocator is exploiter friendly. Please, when you're writing an exploit, use it. And never, never, never use unserialize. This function is a remote code execution, basically. Every time it was in somewhere in a reachable code, it was exploited. So more information you can find in Checkpoint blog, and also in the description of this talk I have a link to the paper I just published. And there's gonna be another publication soon about the vulnerabilities I talk about, more information about them, and also a third vulnerability, which I did not discuss here. PHP bug system is the second link, and there is every bug recorded and every vulnerability. Some of the bugs doesn't have CVEs, unfortunately. And the third link is Nikita Popova, I think I pronounced his name correctly, blog. He's a main contributor to PHP, and he has many explanations about internal mechanisms within PHP. If you want to contact me, so you have my corporate mail, my Twitter, and I'm Yanail on most other platforms, such as Gmail and so on. Couchsurfing, I don't know. So that's it. Any questions?
Thank you, and if you have questions, please line up next to the microphones and ask your question. If you are leaving, please do so quietly. Any questions from here or from the internet? People are overwhelmed. So I'll start with a question, actually, because I have one. I didn't understand the internals too much. I'm interested in applications of exploiting things that you talk about. Have any of this in the wild? Are we expected to see this in the wild?
Actually, PHP7 is not very widely used by now. I think it's 2%. It's just a year old. But as soon as the big platforms, the big CMSs will move to this new language, I predict we will see some of them. Other vulnerabilities, but I assume we'll see more exploits coming.
Thanks. Questions from the audience or from the internet?
Yeah.
Internet has a question, yes.
Okay.
Yes. Are there any popular projects that are affected by these vulnerabilities?
Not that I know of, not yet, because PHP7 is not widely used by now. There are no big CMSs using PHP7. Sorry.
Internet, if you have more questions, then go ahead. Anyone from the audience? Last chance? Okay, so again, please give a big round of applause to Yanai for a great talk.
Thank you.